Morning, Year 9. Right, okay, I'm going to talk through a little bit about atomic structure again, and then we're going to concentrate on this idea of isotopes, okay? So some of this does overlap with what we did in chemistry, okay? It's supposed to, because it leads us into the next bit, okay? So I know it feels a little bit like repetition, but it does overlap, and they can ask you about it on your physics exam, okay? So in terms of the models, remember we started off first of all, Democritus was one of the first people that came up with this idea of atomos, these tiny, tiny balls that everything was made of, okay? But we don't tend to learn that much about Democritus. So we'll start with John Dalton. So in 1805, he came up with some ideas about atomic theories, this idea of what atoms were like, okay? So he said that everything is made of tiny particles called atoms. So he gave atoms their name. Now, he said that they're indivisible and indestructible. So he was the one that came up with this idea of them being almost like solid, like snooker balls, okay? So you can't make them smaller. They are, that's the smallest part that you can have. So they're indivisible and you can't destroy them, okay? And he said that the atoms of each element are the same, okay? So that was a really key idea. So, for example, carbon is only made of carbon atoms, okay? Gold is only made of gold atoms. However, what he did say was that atoms of different elements, in some way, they must be different, okay? So he used wooden balls to demonstrate this idea of atoms. So he recognised quite a lot of key ideas. They weren't perfect, but he recognised a lot of key ideas in our understanding of chemistry, even early on, okay? Then we've got Dalton, okay? Now Dalton came up with the indivisible balls. Then we had Thomson, okay? Thomson was this English physicist who worked with cathode ray tubes, okay? And he discovered the difference between the positive and the negative charges, okay? So he discovered the electrons. So he came up with the plum pudding model. So Thomson is the plum pudding model. And if you remember, what he said was, he stuck with the idea that the atom was a ball, but he said that most of it is a positive charge. So you've got a ball of positive charge, and within that ball, you've got higgledy-piggledy, these little negative charges, these electrons. Okay, so that was Thomson's model, the plum pudding. Then we've got Rutherford. I'll talk a bit more about Rutherford next week, just to recap his experiment. But he did the gold foil experiment, okay, the one that you have to sort of think about. He wasn't satisfied with Thomson's plum pudding model, so he did some more experiments with it, along with Geiger and Marsden. So these three scientists were working together, and he projected a beam of alpha particles, which will make more sense in this unit, at a sheet of gold, okay? So he fired these particles at a very, very thin sheet of gold to try and figure out what is actually going on inside an atom. And his results didn't fit with Thomson's model, okay? So in 1911, his results didn't fit the model, the plum pudding model, okay? So he came up with a new model. So what he said was that an atom has actually got a small, very dense, positively charged nucleus, okay? But most of an atom is made of empty space, okay? So he didn't really understand too much about where the electrons were, but he recognised that most of the mass of an atom, which is still really, really tiny, very, very small, is inside the centre of the atom, okay? And the rest of the atom is empty space, okay? So that's a key point, okay? So you've got this nucleus inside the middle of an atom. Now Bohr was the last one that we're going to think about today, I think, and he came up with the electrons that they are found on these shells, these orbits, okay? So he said that an atom is like a tiny solar system. So the nucleus is in the middle, and then the electrons, like the planets around our sun, are orbiting around this nucleus. Okay, so this is what he came up with, this is his model. So he said that the electrons are in shells, okay, these orbits, these circles. Right, so now we've got our current model, which we call the nuclear model, related to the nucleus, okay? So we've got a small, dense nucleus, that's the bit in the middle. Now this is really, really important. Inside the nucleus, you have protons, which have a positive charge, and neutrons, which don't have any charge at all, okay? Now they are the heaviest of the particles. When we say heavy, it's relative because atoms are so tiny, it's almost beyond our imagination. But within this tiny atom, the biggest part of it, okay, the most mass is made of the protons and the neutrons, okay, and then the electrons are in these orbits. So we know that it's in 3 dimensions, okay, which is why it's not flat. Well, I know it's drawn flat, but it's drawn in a way to try and show that it's 3-dimensional. So that's where the sphere idea comes from, this ball idea. So you've got these electrons in orbit. Okay, now, why is it not moving? Now this bit is just to break down, you don't need to worry about the clock, there's nothing on there that we need to do. So Democritus came up with this word atomos sort of years ago. Much later, in 1805, Dalton came up with this idea of solid balls. Thomson was the plum pudding model. Rutherford was this positive nucleus, okay. Chadwick came up with the nucleus contained protons and neutrons, and then Bohr was the one who came up with the idea that the electrons are on the orbits, okay. So don't worry about that, that's just a bit of a summary. Now, in terms of where things are, you should know where things are. Now, what we need to concentrate on today is the numbers of those things, okay. So we know that our protons are positively charged, our neutrons have no charge, and our electrons are negatively charged. Now, because the protons are positive and the electrons are negative, they cancel each other out. So in an atom, you have to have the same number of protons and electrons. However, the number of neutrons doesn't have to be the same, and that's really important today. So this is what you're going to be working on, okay? So in your periodic table, you've got the symbols of the elements along with the 2 numbers, okay? Sometimes they're the wrong way round, but they've got 2 numbers. Now, the small number tells you how many protons there are in the nucleus, okay? So the small number is the number of protons. Now, by default, because we know that the electrons and the protons, there has to be the same number, it also tells me how many electrons there are. So in sodium's case, it has 11 protons. That must mean that it has 11 electrons as well. Okay, so they have to be the same number. So protons and electrons have to be the same number. So in this case, it would be 11. Now, the big number is the total of what's in the nucleus, okay? So if you go back to this, it's the total number of what's in the nucleus, okay? Now, this is really important today, particularly. We have to be able to work out how many neutrons I have, okay? So if I've got 23 bits, 23 things inside my nucleus, I know that from the small number, 11 of them are protons. So the rest of them must be neutrons, okay? So if I do 23, take away 11, that will give me the number of neutrons, okay? So 23, take away 11 is going to give me 12 neutrons. So it doesn't have to be the same number as the bottom number, okay? Now, this is what's really important today. There are different forms of elements, okay, which are called isotopes. Now, the number of protons determines what an element is, okay? So carbon has 6. I'm going to have to get these right now. Carbon has 6 protons. That's what makes it carbon, okay? Oxygen has 8 protons. That's what makes it oxygen, okay? If carbon had 8 protons, then it wouldn't be carbon, it would be oxygen, okay? So the number of protons is really important. But they can have different numbers of neutrons, okay? So this is where this idea of isotopes comes in. So, for example, carbon has 2 isotopes. Now you can see on there, it's got the symbol, which is C, which is the same. They've both got 6 protons because they have to, because that's carbon. However, they've got a different mass number. The big number at the top is different, okay? Now, in this case, what that tells me is that regular carbon, this is the one that's in the periodic table, regular carbon has 6 protons, 6 electrons, and then 12, take away 6, which gives me 6 neutrons. Okay, so in this case, the numbers are all the same. Okay, so that's just how it works. In carbon 13, okay, it's going to be different. So my number of neutrons is different. So I've still got 6 as my small number. So I've still got 6 electrons. Sorry, 6 protons, which means I've got 6 electrons. 13, take away the 6, gives me 7 neutrons. So in this case, in this nucleus of carbon 13, there are 7 neutrons, which makes it an isotope that we call carbon 13. Okay. Then we have a third isotope, which is called carbon 14. Okay, I'm hoping that you're seeing a pattern in this case now. So in this case, it's got a small number of 6, so it has to have 6 protons, which means it also has 6 electrons. Then I work out my neutrons, 14, take away 6, which will give me 8 neutrons. So the difference in the mass number is accounted for by different numbers of neutrons. Okay, so that is what isotopes are. They have this, for whatever element it is, they have the same number of protons and electrons, but they have different numbers of neutrons. Okay, and you'll see that the isotope is labelled as the name of the element and then its mass number. So for example, the isotope carbon 12, 12 is the mass number. The isotope carbon 13, 13 is the mass number, and the same with carbon 14. Okay, so 14 again is the mass number. Now what you're going to do is you're going to do some practices of using these numbers and getting this idea of isotopes. Okay, so there is a sheet on class charts. It does look quite unwieldy because there's lots of examples, okay, but once you get into the swing of it, you'll find that it's quite straightforward to go through quite quickly. Make sure you read what the question is asking you to do, okay. So the first ones is just really doing a little bit like, let me get back to the right slide, this, okay. So it's asking you how many protons there are, how many electrons there are, how many neutrons there are. So it'll be the big number, take away the small number, okay, and then you're going to do some work on the same idea but thinking about isotopes, okay. So that's your task for today. You will need to probably write it on paper. There won't be any room to write it on the sheet, okay, and then send me a picture.